Okay, so welcome back. Today we will be continuing the mole concept where we have talked about the percentage composition of compounds. So in this case, we first consider a pie, and within a pie, right? How do we go about expressing how much meat there is in the pie? So we can either find out the mass of the meat in the pie, or even express a percentage of the meat with respect to the whole mass of the pie. So this can be the same with compounds. So first of all, the percentage by mass of an element in a compound is generally the mass of that specific element, one of the element, multiplied by the number of atoms of the element. So let's say it's H2O, you have two atoms of hydrogen. So this is one example. So over the whole MR of the component times 100%. So it's like a fraction. So to give you an illustration, let's say you have a basket of fruit where you have apples, and you have maybe um, 4 oranges. Then the question is, so MR of the component is the MR of the MR of the basket of fruits. So it's the mass of the total mass of the fruits. And then what you want to do is when you want to formulate it, it will be the total mass of the basket of fruits. And of course, if you want to find the AR, I mean the percentage of mass of apples, so percentage of mass of apples, an apple in a fruit basket, it will be equals to the AR, so it's the mass of the apple. So let's say each apple is mass of 1 kg or maybe 1 grams, and the orange is 2 grams. Okay, so what we can see is how many there are. The mass of the apple is 1, so mass of one apple multiplied by the number of apple times 100%. So if we want to do a side-by-side comparison, mass of one apple is 1 gram, multiplied by there's 3 apples, over the total mass of the fruits. So you have 1 plus 1 plus 1 plus 2 plus 2 plus 2 plus 2. So it will be 11 times 100%. So it is 3 over 11. If you press your calculator, let me get my calculator. So 3 divided by 11 times 100%, you get about 227.2%. So when we talk about relating it back to the formula, right, when we talk about like mass of the element here is apple. Mass of the apple is the AR of the element. Number, the number of elements means the number of atoms of the element. So it's the number of apple, which is 3 in this case. Then of course the whole MR of the component, which is the total mass of the frequency, times 100%. So generally that's how we get the percentage mass. Okay. Of course, all this you can just pause the video to look through how it's being done. Next, we look into the empirical and molecular formula. Now, empirical formula and molecular formula, they meant two different things. Empirical formula generally refers to the simplest formula of the compound, that means the simplest ratio. And it shows the type of elements present in the compound, and it shows the simplest ratio of the different types of atom in the compound. So when we want to find the empirical formula of a compound, there are a few steps that we need to do. First, we have to find out the mass of the reactants taking part in the reaction. This one usually you can find from the question. The question itself will actually state the values for you. Then we find the relative number of moles of the reactants used. How are we able to find the number of moles? We use the formula number of moles equals mass over MR. So the MR or AR generally is from the periodic table. This one is the mass, which is from the question. And of course, the number of moles is you calculate. Okay. Then from there you simplify the simplest ratio to find the formula of the mole ratio obtained. So over here, let's look at how can you find the empirical formula of magnesium oxide. First, find the mass of the reactants that takes part. 1.2 grams, and then you weigh it. So this is how you go about doing it. To find the mass of oxygen reacted, 0.8 grams. Work it out where this is from the question. To find the mass, followed by the atomic mass, relative atomic mass, the AR, which is from the periodic table. Number of moles is found by the formula, so you calculate. And finally, mole ratio. In this case, when you talk about mole ratio, right, you must always divide by the simplest number of moles. In this particular case, you can see that 0.05 is the lowest number. So when you divide accordingly, right, you'll still get 1. And of course, the formula will be just MgO because of the 1:1. However, when you work with more complex one, like for example H2O, where molecular formula shows the exact number of atoms of each of the element, for some of these components, the empirical formula would have already showed the number of atoms in the compound. So for molecular formula, the empirical formula may not show the actual number of atoms in a compound. For example, your phosphorus 5 oxide, where you could see that the empirical formula is P2O5. However, the molecular formula is P4H10. So when you have to write it down, we can see that P4H10, right, can be divided by 2 for each of the atom, resulting in P2O5. So how is it related is that the empirical formula, the molecular formula is actually multiplied by a common factor to get the molecular formula. Sorry, the empirical formula must multiply by a common factor to get the molecular formula. Okay, and that one way to actually find the molecular formula from the empirical formula is to find that common factor through the mass, the relative mass of the item. So what you can do first is number one, once you have established the relative and the empirical formula, you can find the MR of the empirical formula. After you have find the MR of the empirical formula, you can actually divide the total MR of the molecular formula to find the N, which is the factor. And this N is what you want to find. Based on this N, you will then multiply it by the subscript of the empirical formula to get the molecular formula working. So again, you can watch this. So in this case, it's like if we look at the empirical formula of ethane is CH3. So what's the molecular formula of ethane? Is 30. So what you can do is to find the molecular formula. So first of all, the first step is to find the what is the MR of CH3, which is the empirical formula. In this case, it's 12 plus 3 of 1. Answer is 15. So the empirical formula AR over the molecular formula must give you the N, which is the factor. So you just take 15 divided by 30, the mass, the relative mass. You will see that it's half. Actually, sorry, it's actually better to do the other way, where it's the mass, the relative mass of the molecular formula divided by the relative mass of the empirical formula. You get 30 divided by 15 because the mass of all molecular formula must always be greater than the empirical formula. That's why we use the molecular formula as the numerator and the empirical formula as the denominator. You get N equals to 2, which is the factor. So this would mean that for CH3, the superscript is 2. Never finalize your answer in this way. Rather, you have to expand it out to make it like this. So you multiply because C is 1. So 1 times 2 and 3 times 2, you get C2H6. So this would be the finalized answer. Then next we look into the molecular volume of gas. So for molecular volume of gas, they follow this law, which is the Avogadro's law, where each volume of all gases under the same temperature and pressure will contain the same number of particles. So for example, regardless of the color of the balloon, if they share under the same temperature and pressure and also the volume, they will contain the same number of particles, the particular gas particles within the balloon. So how is this relatable? So very long time ago, someone has actually defined for 1 mole of gas how much volume of the particles is there. So 1 mole of any gas would generally occupy 24,000 cm cube, which is 24 dm cube of volume of the gas at room temperature and pressure. This can only apply for gas. If you are in the liquid form, aqueous form, or solid form, this formula will not apply at all. Therefore, regardless of the chemical compound formula, as long as we follow the number of moles, we will be able to measure the molecular gas volume, provided that it is in the room temperature and pressure. Okay, so what happens if you have different mass here? Same mass, but different components. Because mass doesn't involve number of moles. So what you have to do is based on the mass and the MR or AR of the respective elements, you would then be able to calculate the number of moles. And then number of moles would have to multiply by 24 dm cube to get the volume. So each mass of the gas do not have the same number of moles. Hence, they may not have the same number of particles. Okay. So the key thing is they do not have the same number of moles, and therefore they do not occupy the same the same volume of the molecules. So in a key nutshell, what is the formula that we want to use is that number of moles of gas equals to volume of the gas over 24 dm cube. Okay. And the thing is, it must be in dm cube for your finalized volume. So this would be the relationship between the volume of a gas, number of moles, and the molar gas volume in this case. So if we want it in cm cube, then from dm cube, you have to convert to cm cube, where 1 dm cube equals to 1000 cm cube. So what we can see is there are two ways to calculate number of moles in a gas, whereas we can use the volume over 24, or we can use the mass over MR, where MR is from the periodic table and the mass is usually from the question. You can pause the video to check some of this. Finally, we reach to concentration. Now, concentration, there is two types of units, either in grams per dm cube or mole per dm cube. So in the avenue of solution, we know that it is made of two things, the solute and the solvent. So for solute, it's actually the amount of solid to be dissolved, and the solvent is the liquid in which the solute will be able to dissolve in the solution itself. Hence, when you want to calculate concentration, we are actually measuring the amount of solid or the solute dissolved with respect to 1 dm cube of volume of the solution. That's why the amount here can be represented in terms of the mass, or it can be the number of moles. So because of the mass or number of moles, hence there is actually two forms of formula to calculate concentration, in which in the exam will state very clearly, do they want in grams per dm cube or moles per dm cube. If you are using in terms of moles per dm cube, which is very, very common, then you will need to use the number of moles of the solute divided by the total volume of the solution. On the other hand, if they want in grams per dm cube, usually you use the mass, not the molar mass or the MR, but mainly the mass of the solute with respect to the volume. Okay. So relationship between concentration between mole per dm cube and grams per dm cube, these two formulas can be interconnected by the formula of number of moles equals to mass over MR. So by doing simple manipulation, you are able to actually convert moles per dm cube to grams per dm cube through the division of the grams per dm cube by the mR of the solute. Not the solution, but of the solute. Okay, and therefore you can convert based on this formula, you are able to convert it to the moles per dm cube concentration. So this is in the event the exam wants you to convert grams per dm cube to mole per dm cube, or vice versa. Just take note that the one with the grams per dm cube is the one that is divided by the mR to convert into the moles per dm cube. Okay, just like in this question. Okay, you can pause the video to double check on the working practice. Okay, so that will be the main first part of the mole concept. At the next chapter, we will be talking about how to use this respective formula to calculate to solve problems related to mole cohesion. At the same time, we will also learn how to do some calculation in terms of percentage yield and efficiency, which we will move in the next chapter. Okay, that's all. Thank you.